Hello. Okay, let me begin with showing this result that in the limit pi going to 0, this goes to 6. It's a simple algebra of taking limits and um, um, so p goes to 0 means z goes to 0 because each one of them, all pi going to 0 means each one of them, s, t, and u are going to 0, is going to 0. So limit z going to 0, that's what we are calculating. So if z goes to 0, then this term is large, and you can neglect 1 with respect to that. In the first factor, so this is z equals stu, then square root of 4m squared over z, which means twice m over root z. Similarly, there also we can neglect this this factor. So this is twice m over root z plus 1 divided by twice m over root z minus 1. And that is same as sum over z equals stu twice m over square root z times log 1 plus root z by twice m divided by 1 minus root z by twice m. Now you can binomially expand the denominator. This is 1 minus x to the power minus 1, and therefore when you invert it, 1 minus x to the power minus 1 is 1 plus x and then higher order in x. So higher order in x means root z by twice m. So higher order in like root z by twice m square can be neglected because we have those are going to give higher order contribution, and after multiplying with that, we will have some root z factor upstairs, and in this limit that will go to 0. So we will neglect in the binomial expansion of this, we will neglect root z by twice m square onward. So this will give you 1 plus root z by twice m square. And that's equal to 2 times sum over z equals stu twice m over root z log 1 plus root z over twice m. And log 1 plus x starts with x and then higher order in x. So that gives you 2 times z equals stu twice m over root z times root z plus twice m plus order z by 4m square. And those are going to go to 0. And the first term, the leading term, will cancel this, leading to 1. And summation over z means there are 3 times 3. There are 3 values stu. So sum over stu of 1 will give you 3, and therefore that's 6. Let me now discuss one more renormalization scheme. This one is called minimal subtraction scheme. This was discussed by Tuft and Weinberg, and it's called mass independent. It has another name, which is mass independent renormalization scheme. We will see what that means. So what one does in this case is minimal subtraction means that all these finite ambiguities are simply set to 0. All the finite ambiguities in the counted terms. So therefore, if I at epsilon equal to 0, m over mu, this is what matters, because ultimately you're going to take, these are finite ambiguities, which means they're finite in the epsilon going to 0 limit, and that is the physical limit. This is what is going to appear in all the analysis. So you set them to 0. So as a result, gamma tilde 2 will take the will be given by p square plus m mu square times 1 minus lambda hat over 2 psi 2 minus log m mu hat. So m hat is also a function of mu, because m is the renormalized coupling. That's a function of mu. So I'm making that manifest here. Plus lambda square, or a lambda square contribution. This is just coming from this expression, taking this expression and setting f1 equal to 0. This is just, that's what I wrote here. I wrote there. And similarly, if gamma tilde 4 will be given by this expression with 2g1 set to 0. So minus lambda mu 1 minus 3 by 2 lambda hat mu times psi 1 plus 2 minus log m mu hat square minus 1/3 a s comma t comma u plus order lambda cube. Okay. So the first consequence is that unlike in the previous case, where all these contributions were all 0, and so in the earlier case we had the situation that gamma tilde 2 will be given by m mu square at p square equal to 0, and gamma tilde 4 will be minus lambda mu at all pi, when all pi are set to 0. What that means is that in terms of the effective action, you are looking at constant field configuration, and then that gives you the effective potential. And this renormalized couplings have direct interpretation in terms of the effective potential. In particular, m square is the double derivative of the effective potential at its minimum, and so on. So the effective potential, so you have a direct interpretation of the renormalized coupling in terms of the quantum effective potential. That does not go through, that is not the case here, because now if we set p is equal all the p is equal to 0, then gamma 2 is not gamma 2 has gamma 2 and gamma tilde 2 and gamma tilde 4 are have direct interpretation in terms of the effective potential, but since they are now complicated functions of lambda and mu, lambda and m, lambda and m are not directly, they don't have direct easy interpretation in terms of the effective potential, lambda and mu themselves. This is the first observation, and then the next one is that all these gamma tilde n's, the proper vertices, are finite. They do not have, after choosing this this prescription as usual, they do not have any ambiguities. They're given in terms of the renormalized couplings. But the counter terms, there is an effect of this choice of this renormalization prescription, a special effect on the counter terms. If you remember from our previous discussion, the counter terms have two parts. One is a finite piece, which is finite in the epsilon going to 0 limit, and the residues of and the epsilon poles, and these epsilon poles have residues which are all dependent, in general dependent on masses. So if we can have an expression, let me check. These are the expressions here. Or rather, these are the counter term Lagrangian. Counter term Lagrangian, in fact, in lecture 19, we have written counter term Lagrangian here. So each counter term, you see, there's a pole term, and there's a finite ambiguity. These finite ambiguities are set to 0. All these H2, F1, G1, F2, they are all set to 0 in minimal subtraction scheme. Now, in up to this order in calculations, as we pointed out earlier, that the epsilon pole, the residues are not dependent on masses, but at a higher order, as we have discussed in this here, that at higher order the poles will involve the finite ambiguities of the counter terms at lower order. So it is because of that, since finite ambiguities are mass dependent, it is because of that these epsilon poles are in general mass dependent. However, if you set all the finite ambiguities to 0, as is done in MS scheme, there will be no mass dependence, because the mass dependence were entirely coming from the finite ambiguities of the counter terms. Since they are all 0, all these A0, A's, k coefficient k equal to 0 to infinity, all of them are mass independent. Similarly for B's and C's. So that is, so therefore, so the next observation here is that that residues of epsilon poles in all counter terms are mass independent. Now, there is a way to understand this. You see, the mass dependence of these residues, since they are inflicted by the finite ambiguities of the counter terms, this is not actually a real physical. There is no physical. This dependence is not physical, because it depends on your choice. In fact, now, since we are choosing this finite ambiguities to be 0, the mass dependence goes away. Another way to understand this is the following: that the epsilon poles are representative of the UV divergences, which are coming from the large momentum region integration, coming from the integration in Feynman diagrams in the large momentum region. And when you take all the momenta to be very large, then you can neglect all the masses in the integrand, and therefore the portion of the integral that includes large momenta are supposed to be mass independent. So that is why there is no physical reason why these residues, which are basically the divergent pieces, should be mass dependent. So this mass dependence is basically a fake dependence because of the finite ambiguities of the counter terms. So this is a simplification, and a crucial simplification, in fact, because now all these coefficients, A, B, and C coefficients, are mass independent. This is going to be important, as I shall discuss now, in answering the question of how the renormalized parameters, renormalized couplings, depend on the scale. So as I discussed in the previous slide, that once you fix the renormalization prescription, then that defines the relation between gamma tilde 2 and gamma tilde 4 and the renormalized couplings without any ambiguity. You are basically, by fixing renormalization, the renormalization prescription is basically fixing that ambiguity. And now, once that prescription is fixed, there is a precise specific relation between the proper vertices and the renormalized couplings without any ambiguity. And therefore, the observables, which are written in terms of proper vertices, have a specific relation with the renormalized coupling without any ambiguity. And therefore, you can do a finite experiments and to measure these observable, and as a result, you can find the renormalized couplings. Of course, this is not an exact procedure, because you know the observable in terms of the couplings as a power series in lambda, because it's a perturbative calculation. So you truncate that, and that means that you are working in particular level of approximation. But within that level of approximation, you can certainly calculate the renormalized. You can certainly calculate this relation between the coupling, the renormalized couplings, and the observable. Now, once you know this at a particular scale, then at that scale you can predict all the other observables. But the question is that how will you change when you go to a different scale? Do you have a prediction, or do you have to do it at every order, at every scale separately? But since if the theory is complete, and then one would expect that one should be able to know once the couplings are known at a particular scale, it should be possible to derive the couplings at a different scale. That is what we're going to discuss now, and it is in that context this particular scheme is very helpful. It simplifies the problem, and the different schemes can be good for different purposes. Like in the first case, we have a direct interpretation in terms of the effective potential of the renormalized coupling, so the direct interpretation in terms of the effective potential. And in this case, it is the running of the couplings when the mu scale changes, and the running of the coupling with that, the finding that running is simplified in this particular scheme. So I shall now discuss this question. So the question is, how do lambda mu m mu and the observables P1 to Pn lambda mu m mu, which has an explicit dependence on mu, change as the scale mu changes. Now, these physical observables, I mean, finding the change is equivalent to knowing the changes, how the proper vertices slide with respect to the mu, with respect to the scale mu. Okay, so that is equivalent to doing that. The general idea to answer such a question is as follows. First of all, relate renormalized quantities to the corresponding bare quantities which are mu independent. Then next, apply the operator mu dd mu on this relation. This dd mu is a total derivative, which means it acts both on explicit and implicit dependence on mu. And because of this, because of the mu factor in front, mu dd mu, it does not affect the mass dimension of the quantity on which it is acting. Then that will lead to a differential equation involving first order differential equation involving the couplings, and one solves that. One has to solve that equations for running couplings. But this solution, so far this is general, but now when one solves this equations, one should solve in after fixing the prescription, renormalization prescription. So solution should be attempted after fixing the renormalization prescription. That's because the renormalization prescription has some finite ambiguities. You can write down the differential equations including those ambiguous terms, but you cannot solve them. Once you fix a prescription, remove the ambiguity, then only you can solve them explicitly. So now, as I said, that these ambiguities are all set to 0, and therefore the coefficients A, B, C coefficients which appear in the relation between the renormalized and bare quantities those relations are simplified, become mass independent, I shall consider MS scheme now for solving to solve the running of lambda mu. So that's what I'm going to do now as to demonstrate this procedure. Define beta lambda to be limit epsilon going to 0 mu d lambda d mu. Then consider the first step of relating the renormalized and bare couplings, and the relation is given by this equation. So since we are considering lambda, so it is this, the relevant equation is this one. Now in order to do that, one needs to know the coefficients a0 and ak. First of all the coefficients have mass dependence in general, but in this scheme, as I mentioned, they are, as I explained, they are mass independent. So ak will be only lambda dependent. If also a0 is only lambda dependent. Now, for the lambda phi-fourth theory in 4 dimension, we have done certain calculations. Let us look at that results, how far we have calculated it. So recall the let us first recall the general structure of this is where general structure of this Lagrangian. So this is the renormalized Lagrangian, which is given by L plus L counter term. This counter term is what we have calculated to some extent, and this renormalized Lagrangian density is where this lambda 0 appears. This is the bare coupling. So that means this lambda 0 can be read from L plus L counter term. This is what we should do. So L has originally a term lambda mu to the power epsilon by factorial 4 phi to the power 4. Let us now look at the structure of the definition of lambda 0. So lambda 0 appears in the renormalized Lagrangian, as I pointed out just now, and this is given by 1 plus c divided by 1 plus a whole square times lambda mu to the power epsilon. Now these capital A, capital B, and capital C are the counter term Lagrangians. Okay, different parts of the counter term Lagrangian, where we have to set all the finite ambiguities to 0. So that means only the pole terms, the bare minimum pole terms, are kept in this. Therefore, this A is a pole, and if you do a binomial expansion, 1 plus a to the power minus 2, the leading term will be 1, and then there will be pole terms, and multiplying that with 1 plus c, there will be a leading term which is 1, and therefore the structure of this will be 1 plus pole terms. So that 1 multiplies with lambda mu to the power epsilon, and that must be giving this first term. So since mu to the power epsilon is set aside, a0 is nothing but lambda. Okay, this just comes from the fact that had we not chosen this MA scheme, we would have all sorts of dependence on um, um, because this A will not be a pure pole term. It will have finite finite ambiguities, and after choosing a prescription, those ambiguities are fixed, but they are non-trivial functions, and they will multiply with lambda mu to the power epsilon after taking the binomial expansion. So the non-pole term, the finite term here, which is A0, will be more complicated in that case, which is not the situation here. So what I just argued, that A0 is going to be lambda. Then we have to calculate AKs also, and let us see how far we have in our calculations done earlier, how far we have calculated these poles. So capital A has been calculated with this simple pole of order 1 with at an order lambda square. So when you do 1 plus A to the power minus 2, then you have a lambda square contribution, lambda hat square contribution. In the binomial expansion, the first term, this 1 plus A to the minus 2, the first term will be 1, then the second term will be lambda hat square times 1 over epsilon. So there will be a pole of, so this contribution will be 1 plus some coefficient times lambda 1 plus some coefficient times lambda square times 1 over epsilon. It is a pole of order 1, but with strength in the lambda expansion, it is lambda square. Since there is a lambda sitting outside, it will be of the order lambda cube. This will give you a lambda cube contribution to 1 over epsilon residue. So that means that term 1 plus A to the power minus 2 multiplied by this 1 will give you A1, the lambda cube, order lambda cube contribution in A1. That is how we have to calculate it. But is there any lower order contribution? There is a lower order contribution where this starts with 1 plus, as I just explained, the coefficient lambda square by epsilon. But this 1 multiplied with C will give you a lower order contribution because C is order lambda. So this is what you can see here. So the C has a pole of order 1, but at order lambda. So that term will give you order lambda contribution to A1. So we have basically calculated A1 up to order lambda square. Okay, so let us collect all these results and write it down here. So the relation between the bare coupling and the renormalized coupling will be given by mu to the power epsilon times A0, which is given by lambda, plus sum over k equals 1 to infinity ak lambda divided by epsilon to the power k. Where in our calculation, we have calculated A1 as I just explained. The leading order contribution in A1 is coming from C multiplying 1, and C has lambda 3 lambda hat over epsilon, and there is an overall factor lambda mu to the power epsilon. So this is 3 lambda hat over epsilon times mu to the power epsilon. Okay, that's the leading, that is lambda square contribution in A1, right? And then the contribution coming from A, which is subleading in this binomial expansion of 1 plus a to the minus 2, will give you lambda cube contribution to this relation. So let us stick to this. This is mu to the power epsilon times 3 lambda lambda hat over epsilon. So that is what the value of A1 is. So A1 is mu to the power epsilon is already outside, has been taken outside, and 1 over epsilon. So A1 is 3 lambda lambda hat, 3 lambda lambda hat plus order lambda cube. And lambda hat is lambda over 16 pi square. So this is 3 lambda square. So this is nothing but 3 lambda square over 16 pi square plus order lambda cube. Now, if we, so this is what, so that we have just performed the first step in this procedure, the relation, and now I apply mu dd mu on this. Mu dd mu on applying on lambda 0 is 0 because lambda 0 is independent of mu. So so the relation is mu dd mu acting on mu to the power epsilon times lambda plus sum over k equals 1 to infinity a k lambda over epsilon to the power k is equal to 0. The first term, when this operator acts on the first factor mu to the power epsilon, it gives epsilon mu to the power epsilon lambda plus k equals 1 to infinity a k lambda by epsilon to the power k plus mu to the power epsilon times mu dd mu acting on this factor can be written as mu d lambda d mu times 1 plus sum over k equals 1 to infinity a k prime of lambda divided by epsilon to the power k, where a k prime is d a k d lambda. It's a prime is a lambda derivative d a k d lambda. Now this quantity, this mu d lambda d mu, given that lambda is a renormalized quantity which is finite in the epsilon going to 0 limit, so therefore this must be finite or analytic at epsilon going to 0. So finite as epsilon goes to 0, and therefore I should be able to do a Taylor expansion. If you did the Taylor expansion, then mu d lambda d mu at epsilon equal to 0 is what I defined as beta lambda here. And then the next term will be epsilon times another function beta 1 of lambda. That's the definition of beta 1, which is basically the epsilon derivative of mu d lambda d mu at epsilon equal to 0. Okay. I shall next further analyze this question in the next part.